Let's discuss. Well, first we need to understand why we need to do that. Like, why the hell we need to clean text corporas, why we need to train our own LLM. And after we figure it out, we need to understand how we can do it fast, because, well, text datasets are quite big and large models are, well, large. So we need to process it really fast and not like in years. And, well, yeah, we'll discuss and see how noisy public corporas are and how it finally affects the model. Like, if it doesn't affect the model or any costs or something, why we do it, actually. So, yeah, just quick setup. We at Tochka, we train our own in-house LLM, and we need it because we have a lot of sensitive data and we can't like process it via OpenAI or something, so we need a in-house LLM. And yeah, we train it because basically all the open source LLM models like Vans are not really good with Russian. And we are like Russian talking company with Russian customers, so we need to fix that. And yeah, we have a model, let's say that's Qwen, and we want to improve it. And well, there are multiple ways how we can do it. We can do it via like changing model architecture and doing something around it. We can change it via, like, we can change the process of how we train our model. But last and not the least, we can do something about data. And that's the key concept, and that's what the talk will be about. So, talking about data, how we can via data help our model? Well, first we can just use more data. Actually, usually it works, especially for classic ML models. If you have more data, well, that's possible that you will have like high accuracy because you have more data and you're like more data-driven in some sense. And for LLM, usually it works the same way. But yeah, if you can't like get any more data, then you have another way. You can just clean the data you already have, and you can, with a smaller amount of data and smaller training steps, like get this like the same results or even better results. So that's the second way that we're gonna pursue today. And yeah, quick setup. Like we are doing like this step of training large language model, which is, well, quite like pre-training. That's not like fair pre-training, but that's language adaptation, which is actually the way that we try for vectors in English for the same words look the same way that like for the same like translated Russian words, vectors will look. So what I'm trying to say is like we want to model to think in Russian the same way that it thinks in English. Yeah, and for the hardware, we have like one cluster, we have like 800, and we have 800 millions of text, so we need to live with it. Yeah, and why we should do it? Like where this idea of cleaning the data and getting a better model comes from. Well, when we are thinking about a data set for training large language model, what characteristics it should have? Well, first, it should be large. Yeah, with no data, you cannot train large language model. And it should be diverse because, well, large language models are really good at overfitting, and we don't want our model to overfit. So we need to like diverse data with no duplicates or something. And there shouldn't be trash. Well, on pre-training step, we try to train a model so it can capture like basic structures of a language, and well, it should talk like with a proper grammar, with a proper like structure of sentences and something. So we don't want to have any unstructured text. Like we don't want this text mess or random sets of words or something. And actually, there are even some research that says that, well, if you like clean your data before training your large language model, then as a result, your large language model is going to be better. Well, that's not like a strange outcome because like we already know this from classic ML that you need to work with your data and curate it. But when like large language models started to emerge, everyone was like, we're gonna like put all the common crawl here and everything will go fine. But well, after this, like people started like serving it, and finally it turned out that, well, no, you need to clean it. And to clean it, let's discuss what we should clean. Like what text we want to remove. And first, like, yeah, here is advertisement. We don't want a lot of advertisement. In advertisements, they are like names for the products, and they are, well, we don't need to produce them. We don't need to generate such text. We can see this word, well, name of a product, like only once, and well, maybe not once if that advertisement is multiple in our dataset. But yeah, you got what I mean. We don't want a lot of advertisement in our corpus. And here are some other categories we don't want, and obviously that's idle content and safe content and hidden text. Why they go together? Just look at this text. Like I didn't translate it totally in English, but I will like explain what happens here. like we have these texts, and if we try to read them, we see that there are some texts like about dancing collective, about cooking, about culinary, something recipes, well, yeah. But if you look a bit closer, in between these texts, you see porn-related text, and we don't want it. And if you try to like read all text, it turned out that it's like it doesn't make sense. Like it's a random words, and between them, some words that are, well, bad. We don't want to learn to train our model on it. And how this happens, like sites who like want to provide this obscene or adult or unsafe content, they just they add some words that are not related to the topics they are advertising. So like browser doesn't ban them, like so they don't get banned because they have some normal text on these sites, but users don't see it because it's like invisible, made another color, or just not visible. But when OpenCrawler opens this site, it is like, oh, okay, it's normal text. I'm going to crawl all this, and as a result, we have this messy text, and we don't want it. So yeah, but quick disclaimer, we don't want to remove all this text. That's okay for us that we still have some obscene text in our corpus, just because if the model doesn't see any obscene lexic at all, then the model don't know how to classify it. Well, a model that never like saw this like strong Russian language with obscene words, it's like if we tell the model that like, please don't use the strong Russian language, and if user tries to use it, don't do something about it. And the model can't handle this task. It can't classify if it's like bad or not, because it just haven't seen this. It is like who is more prone to like tell a secret, a child that who doesn't know that like this is a secret, or an adult who knows this information fully but understands that you can't talk about it. So we want an adult, we want a model that knows that this text exists but don't produce them. So yeah, and the last but not the least, we want to remove all the duplicates, because yeah, we want really various text, so our model doesn't overfit, so we want to get rid of all the duplicates. Yeah, so if talking about like business metrics, of course I mentioned that generally we want a model with higher quality, but not only that, there is also some business impact. If we like get less data for LLM training, then we need less steps. And that means that we also speed up our training process, and also we reduce the cost, because we need less training hours. So yeah, now that we like get the idea why we should do that, why we should like clean large text corporas, we need to discuss how we can do it. And for understanding how to do it, there are also some surveys. Like, we are not the first company to do it. There are many companies who do that, and they publish their surveys. And if you read all that, there are multiple steps, there are multiple approaches to do that. But if you try to summarize all that, there are like 3 common steps that happen like in every approach. There is always something about cleaning artifacts, something about filtering some documents that we consider as bad ones, and there is always something about duplication. So let's stick to these 3. And talking about the data that we're going to filter, I propose that we use CulturaX. It is one of the data sets that is multilingual one, and it is marketed as a cleaned, curated data set. Like, they even say that it's cleaned. Like, yeah, we should believe them, but actually not. That's going to be like in the end of this talk, we're going to like take a look how much trash it contains actually. And also we will go through FindWeb 2, which is like more widely used, I would say, than CulturaX, because it's just a more modern data set. But that's like in the end, we will for now we will stick to CulturaX, and in the end we will also see statistics for FindWeb. So for CulturaX, you also can see that like English dominates all other languages. Like the half of this data set is English, and like for the Russian, it is only like 1/5 of what English is. And for Armenian language, it's even less. So if we are working with a language except for English, there is a problem that we don't have a lot of data at all, and we need to figure it out somehow. So if you don't have a lot of data and you just can't get more data, you need to work with the one you already have and like filter it judiciously. So that's what we're going to do. As a start point, we have this CulturaX, and it is like 800 million texts. So let's start doing something about it. And the first thing we need to do is remove parsing artifacts. And when I'm talking about parsing artifacts, that's what I mean. Like you can see an article, and in the left you can see that, well, caption is doubled, and in the end we have this strange link, this like meta information, and we don't want it. Like it makes us, that makes the text less integrated in this. Well, it's not a proper text. We don't want our model to generate this, so we want to remove it. And well, how we can do it? Of course, we can run some human assessment. Like we can ask humans to delete these artifacts for every text, but that's really expensive and slow. And the same thing applies to LLM. You can also do this synthetically, but it's also slow and expensive. And here comes the third approach. We can train some model specifically that can be lightweight transformer model, and it's gonna solve these tasks like sec to sec, sequence to sequence, or searching for named entity recognition. You can treat these tasks like that. So yeah, and that's fast and that's cheap. Once you need to train the model, and after this, this process is getting quite cheap and fast. And how we can do that? Well, of course, we need some data, and for that we need some synthetic data. So basically, we still write a prompt for ChatGPT or something, so we can get this data on which we can train. And after that, we simply train our models. It can be named entity recognition or sequence to sequence. And as a result, we have a model that does the same thing as ChatGPT could do, but it's cheaper and faster. And after that, yeah, we try to apply it to our Corpora, to our corpus, and as a result, even after this step that isn't meant to get rid of some documents, it is just meant to make the documents cleaner, clean some parts of the documents. But even after this step, we get rid of some documents, because some documents in CulturaX, well, are simply caption and a link, for example. So some documents fail to pass this stage, and we already have less data. And yeah, when our texts are quite clean, we've got rid of all this trash, we can proceed to filtration. And talking about filtration, well, let's define what it is. When we want to filter on a corpus level for each document, we want to have a label. Should it remain or not? We want it to remain, or we want to remove it. And yeah, one important thing that we don't care about recall. As I said, it's fine if we have some obscene text, some bad text, because it helps model classify these texts. But we want fine precision. We don't want to get rid of any good data, because we don't have a lot of data, so we don't want to lose it. So we concentrate on precision, and we need this binary label. But actually, that shouldn't be really binary. I mean, it's better if we have separate criteria for this, because it's quite difficult to define what we can treat as a good document or bad document. So we need some criteria based on which we decide is the document good or bad. So yeah, and also we can turn off, turn on this criteria, and use different thresholds for different steps, all this cons, pros and cons, well, mainly pros. Advantages, that's what I mean. Yeah, so let's discuss what criteria it could be. And here we again can look at what people in industry do. And Red Pajama, that's a dataset that was used for training Llama model. They come with this version. They propose that we have some heuristics that filter out all the text where we have too long words, too short words, too many sentences, not enough sentences, something like that, just heuristics. They come up with text repetitiveness and with harmful text, yeah. But it works quite easily. They just keep a set of words that they treat as obscene, and they're if the text contains more than 10 of such words, then the text is bad. So yeah, quite straightforward. And the fourth criterion is quite interesting. First three, they're just statistical ones, that's heuristics, and the last one is model-based. The last one they call Wikipedia likeness. It is how much our text looks like Wikipedia. That's quite a strange criteria, but what they mean here is that we want really quality text with high quality, some good text that looks like Wikipedia articles, and for that they use fast text model, which is quite old. We definitely want something more modern that can capture more sense from the text, but let's stick to this for now. And first, let's figure out these three criteria, which are heuristics. And yeah, they are already implemented, like all the repetitiveness and statistical and harmfulness. Red Pajama is actually open source framework, so you can use it and you can like use it on your own text, on your own corpora, so there is no problem. But the problem is that they have these thresholds, and these thresholds are chosen for English, and every language has its own English. Like, it's not its own English, its own thresholds. What I mean is every language has its own like average length of word, average length of sentence, and so on and so on. So these thresholds, they work fine for English, but they fail to work for another languages, and that's one of the reasons why for another languages like CulturaX, FineWeb, and other corporates, they are not quite fine because thresholds were chosen for English mainly. And the challenge is to find these thresholds, and yeah, how you should do it for your language you want to train a model on is by exploring the distribution of your labels, for example, of your scores, I would say. So you use these heuristics, you run them like on the top of your corpora on your language, and then you just look at the distribution, and based on this distribution, you can make some outcomes, like we need to like get rid of all the tags that fall like less than 7 or more than 1,000. For example, for this statistic, which is mean number of words by line, if we look at the tags that are less than 7 by this score, then we see mainly caption, ads, or some just goods descriptions. So we don't want to see that because that's not wholesome text that we need to train the model to be able to produce like a clean Russian text. So yeah, that's just a slide with a like batch of statistics. Probably you don't need it, but just in case, if you're going to look at this PDF and try to reproduce what I'm talking about, yeah, everything is reproducible. That are statistics for like Red Pajama heuristics for Russian language. And yeah, after this stage, we already get rid of like 20% of CultureX, and you're looking at that and like CultureX, you are like curated dataset. Why this happens? Like simple heuristics, and they get rid of 20% of the dataset, and that's just crazy. Yeah, but here we still have like this fourth criterion, which is about Wikipedia likeness. And actually, why Wikipedia? What does it mean? Like, if the text looks like Wikipedia, why is it good? Actually, what is special about Wikipedia articles? And we can debunk it in 3 criteria, which are actually integrity, factuality, and truthfulness. Well, let's discuss them. And all together, they make like this specific thing that is special about Wikipedia articles, that they are quite credible. Well, then integrity is about the thing that we have like wholesome text. It's not a list, and it's not just a random set of threads or something. We can like give it a title. And well, we want to work with this text because that help our model produce wholesome texts. The second thing is factuality. We want our text to be rich in terms of facts, so like our model can handle some information about the real world from it. And also there is a criterion about truthfulness. So we want this text to be like not about like red grass and green people working on it, but about some real facts. Actually, we didn't use that one in a final version, but if we are trying to reproduce what Wikipedia likeness looks like, that also should be on the list. So when we have decided which criteria we should use, let's decide how we can assess it. And well, approach looks like in the case when we were trying to get rid of the artifacts, we still like make some data using ChatGPT or something, and then we just use it to train our own model that is fast and cheap and so on. But the one thing that we should change is the model architecture. We can just simply, well, run with any encoder, try, well, we can, but there is one architecture trick that's gonna help us a lot in terms of quality. Well, if you are thinking about like training classifier based on encoder model, the most obvious thing you would do, you would just pull the vector from the like first CLS token and then just map it to the labels. You will have some classifier hat on the top of this pooled CLS token. But if you like try thinking about it, it is like this vector should contain enough information to predict like 3 labels. And this is, well, a lot of information, especially if you're talking about different labels. Well, I mean, like if they are not connected or something, like they have opposite meaning or something. So it would be quite nice if we could like capture all this information, not in one vector, but in different vectors. So what I propose is to change the way we like format the data before training our encoder-based classifier. So we have multiple CLS tokens. And so that is possible that we like just pull every CLS token for every specific class. And that's the way that we can like easily increase the quality of our model without changing anything about like architecture. We simply change the way that we treat the data. And well, okay, in terms of architecture, we like change it just a bit. We change the way that we pull the vectors. And that's all actually. And yeah, that helps us in terms of RockOak, for example. RockOak goes, well, a bit higher if we do that trick. So that's just a good and fast solution if you want like multi-label classification encoder-based model. Yep. So, and for the terms of threshold, when we have trained this model, we can also like assign some thresholds, and especially this model, which like captures integrity and factuality, it helps us get rid of some ads that were not filtered out on the previous steps, and also it helps us like get rid of like lists of contacts or just locations. For example, that's common for these logistics businesses who like we can transfer your things from one city to another, and there is a wall site like just listing cities or something, or listing goods that the company sells. So we want to get rid of this text, and this like this heuristic, this course produced by model helps us do it. And yeah, after this step, we also lose like a solid amount of CulturaX. Actually, one important disclaimer that like this heuristics filtering and text quality filtering, they happen at the same time. So some samples, well, I mean, they run in parallel. So some samples come into both categories. So that's like that person's written on the right, they just simply like add up in a sum number. They also can intersect. So like later on, we will look at the final percent that we get rid of. But yeah, just keep it in mind. And yeah, also that's possible that in your company you already have some models that can assess text in terms of how good this text is. Maybe you like you can use it for moderation, for example. I suppose in many companies there are some models that can do moderation, like if the text is obscene or something. And well, you can reuse them when you are filtering a text corpora. You can like run all the scores at top of that and use this scores. And in our case, that was true. We had a guardrail system that produced scores for like text. Do they align with our tone of voice? And thanks to this model, we were able to get rid of many specific categories we couldn't get rid of on previous steps. For example, now we are able to get rid of debauch threats. For the funny examples. And also like some toxic comments and some topics we really don't want to see in our corporates. And after this, we get rid of not so like, that's not a big percent of data, but actually it's really important because like quite bad text fall into this category, and we definitely want to get rid of them, especially the ones like in terms of nationalism or something. And on this, like, at this point of time, you should have a question like, how do you do that if you use like transformer models for all your filtration and you have like 800 million of text? How do you do that? Like, it should take like days, months, or something. But actually, you can like optimize it. If you are working with transformer models, that comes up as a GPU-bound job, and you can like run it in parallel and you can optimize it. So if we run it via accelerate plus on an extra time and top it off with I/O bindings, then everything goes fine. And actually, we can do these computations in like 90 hours, which is not relatively big, because, well, we need to clean this corpora once, and then we can run like model training multiple times on the top of it. So that's a task that we do once. So that's fine if it like works for 90 hours. And yeah, getting back to our pipeline, we have already cleaned the artifacts, we have made some filtering, and so now we need to think about the duplication. And talking about the duplication, there are just, well, two ways how we can do it. We can do it like text-wise or sense-wise. If we're talking about text-wise, then we are searching for common substrings or something. And if we're talking about sense-wise, then yeah, we are looking for texts that are like similar in terms of sense. And we want to get rid of both of these similarities, but well, text-wise is more straightforward. Let's start from it. Like, that's a task that was solved like, 10 or 20 years ago. It's just a classic task. And for that, we can use hash plus ls hash. I suppose I can just fastly go through like how it works. So document is split it into a set of n-grams. Then for every n-gram, we like count a number of hashes. And then for each of hashes, we choose minimum among all the documents in grams. And so every document becomes a vector. And with these vectors, we can do what is named like hash. And hash helps us like find some strings in vectors, if we can put it this way. What I mean is we split our vectors in some buckets, and we use these buckets as a keys. And if we see that documents have like common buckets, that means suppose that these documents, they have like a lot of common substrings, and we can get rid of them. So yeah, for the parameters that we used 5 grams and counted like 256 hashes for each, and yeah, that were buckets of size of 8, just in case. That's also for, if you want to reproduce it, you can use this. You can use that numbers. Yeah, and well, we figure out how to do this text-wise deduplication, but we still have a sense-wise deduplication, and that's a bit trickier because, well, the task isn't difficult at all. Like if you think about sense-wise deduplication, well, we need to represent our text somehow, and then we need to find the similarities. But that's also the task that has its own solutions. We need some embedder, and we have some vector DB, so, well, the task is solved. But no, we still have like 800 million of self-texts, and if we run it so straightforward, it works too slow. So we need to do something about it. And there is a solution. We can run this in a sharded setup, and if we do some modifications, what I mean, if we use IVF index, which is like, you can see it as a splitting in Voronoi cells. Like we split all of our index in cells, and then we search like in a specific cell, we find the most needed one or in neighbors of this cell, and it makes it all faster. We still like can fail sometime, like it's not the most precise method, but it's fast and it works fine for our corpus. So yeah, and that way we can like compute all this quite fast. Like all this deduplication runs in 20 hours for our like 600 million of texts, and that's quite fine. And as a result, we have some like duplicates in terms of text-wise and some duplicates in terms of sense-wise. And how we can handle it? Like we still need to get rid of duplicates. We can treat both like, well, for both cases, we assume that we have some pairs of duplicates. If we assume that we have pairs of duplicates, then we can treat it as a list of edges. And if we treat it this way, then we can see it as a graph. And in graph, we can see some connected components. In these terms, like every connected component can be treated as a cluster. And this cluster, well, there are duplicates. So one cluster is a text that are similar, and we want to do something about it. And talking about clusters, they fall into 2 categories. So we have something that we can call bad clusters and good clusters. So if we see a cluster and there are texts that we, on the previous steps, on filtration steps, like assigned as like bad ones, so we don't want to see this cluster because we suppose that all the elements in this cluster, they are bad. So we just drop this cluster. And if we don't see any like bad examples in one cluster, then we treat it as a good cluster. So we just like leave one, or well, that's a threshold stuff. So we can leave more, but well, we definitely want to get rid of the most part of the cluster. In our setup, we just left one element of good clusters, and we totally like drop bad clusters. So yeah, and after this step, we also like get rid of some data after the filtration. So it also helps, especially in terms of like preventing overfitting. And the one thing is, we don't want to simply like deduplicate all the full similarities. We also want to do some topic rebalancing, because talking about variety in terms of text data sets, we want to like balance topics a bit, and it also helps like overall model performance. So what we do, like we already have vectors from previous step when we tried to find exact similarities, but now we want true clustering. We don't want this like workarounds with graphs. We want true clustering. But all like many clusterization algorithms falls like they don't work fine with a lot of data. So we need to figure something out. But one like clusterization algorithm that works fine for big data sets is Birch. And talking about Birch, the default sklearn implementation actually works quite bad in terms of running on multiple texts. I mean, large amounts of text, because it is quite bad optimized for running on multiple cores. So we needed to do something about it, and as a result, we have rewritten it in a PyTorch setup. So now it works fine, and now we can do it in 20 hours. So just one more day to get through all our corpus. And it also gets rid of some data. I would say the same amount as with duplication. So it also works fine. Well, if you are curious, the most popular clusters in CulturaX are movie descriptions and ads. And what we get at the end of the day, after all the intersections filtered out, we get rid of 40% of all CulturaX. Just imagine 40% of a data set that is marketed like a cleaned one, curated one, just falls in the categories of being ads or captions or hidden text or unsafe content or something. So when we get rid of all of this, we can train a model on what is left. Just some statistics of FineWeb. FineWeb is better in some terms, less text fall into these heuristics, less text fall in problems with text quality, with tone of voice. But for the duplication, we've got rid of more text, but that's not just because FineWeb is worse, but because we were a bit more conservative about thresholds in the duplication. Because when we were working with FineWeb, we were training a larger model, and we needed more variety because the model was even more prone to overfit. So generally speaking, FineWeb is better, in the general quality of the data set. But on this graphic, we get rid of even more data, talking about FineWeb. And if we talk about the results, when you do all these steps and trying to train the model on it, it converges better. Well, the loss is going down faster, and the final quality is also better. Which is fine. We save some money because we don't need so many iterations, and we have a better model. So everything we wanted to achieve, we achieved doing that stuff. And talking about the final quality of a model, it's also fine. Just one disclaimer: we are not a research company, so that's not a really quality ablation. What I mean is these results were achieved thanks to many approaches we tried, including these modifications with data, and including some modifications with architecture and training cycle, training loop. But as a result, we were able to train Qwen to 235 billion parameters, the way that it outperforms GPT 4.1 on our tasks. That actually are all the graphics. Now we even perform even better. So for the company and for the company's tasks, it works quite fine. And this tinkering with data is one of the points that helped us achieve it. So that's quite important. And we can do it quite fast, which is also a heavy plus. And at the end of presentations, maybe some of you have this question, why did I listen to all this stuff if I never do pre-training? And I have answer for that actually. If you are not doing pre-training, you still may do some soft fine-tuning. And for soft fine-tuning, you actually have the same problems. What I mean, you have to do all this, cleaning artifacts and filtering the duplication. So all these approaches can run not only on pre-training steps, but only on SF-test step or preparing data for reinforcement learning. So whatever you do with language models, or maybe you're training some embedded models, that also works. So in terms of SFT, you still have the same problems about clean artifacts. Well, you have meta-prompt leaks, you have bad reasoning traces. For the filtering, well, there are some answers where a model is oh, I don't know, but if I would try to solve this, I would do this. And that's not that's not the answers that we really wanted. We want to train on answers where we are quite sure. There still can be some dirty, naughty answers. There can be cases where we were trying to tune our model so we don't fall to red teaming. So when the user asks to do something that we don't want to do and prohibit in system prompt, model sometimes can follow what user is asking for, and we don't want that. We want to filter out these answers and these samples. And the same thing about the duplication, like variety of the data is important on all the steps of model training. So yeah, and like to summarize it all, like curated data sets are not so curated. So you have to filter them. Then data filtering speeds up model training, and the final quality is also good. Like you can read it from surveys that already exist, but like this talk is just one more proof that it actually works. And yeah, like garbage in, garbage out, no matter what you're training, is it a classic ML model or is it large language model, you should take care of the quality of your data. And that's all. It was a bit like faster than I planned, but yeah, I'm ready to answer your questions. Yep.
Hi, Elizaveta. I've recently gotten into data science, so this might be a bit of a silly question, but do you think it will be possible to change the obscene Russian language into a more family-friendly version, and then that be used in the training itself?
Could you please like repeat the end of your question?
Yeah. Could you possibly convert the obscene Russian language into a more family-friendly version and then have it be used in the training?
Using training, you mean like you don't want to get rid of the samples with obscene Russian language and just like translate them in family-friendly and don't get rid of the sample, but just fix it and
or
use
just
it.
Get an additional data by translating?
Well, yeah, I suppose that's possible. Like we can do it. Well, if we don't have a lot of data that we need to do it on, we can simply use some prompting approaches. Like you will see like a text with strong Russian language, and you have to produce like the text with the same meaning, but like written more polite correctly. So yeah, it got to work, and we don't need to get rid of these samples. And yeah, the second approach is like if we have a lot of data, we need to do separation with. Then we can yet like train this transformer model that will do the same thing based on synthetic data, and yeah, so that's totally possible.
Thank you very much for your presentation. My question would be a little bit different. Do you have any experience or what you know about doing all this stuff for languages that are less popular? Like Armenian or because, you know, English and Russian, those are very popular languages, so you can find a lot of content. But what about less popular languages? Thank you.
Well, I would say in some terms, well, first, you should work with multilingual models because, well, there are some common roots in different languages. So if you are trying to work with like low source languages, you definitely need to work with multilingual models because they know something from another languages and they can reuse this knowledge based on your language. And I would say you can do like the same thing that I'm talking about language adaptation. Yes, it's more difficult because you have less data than, for example, in Russian, but we met the same problem. Like we tried to like make, well, vectors for English words and corresponding Russian words closer. And I suppose that the same approach can be experienced for Armenian, and yeah, you have less data, but you may think about some augmentations, and it can be produced by human assessors, I suppose, and then these human translations, I would say these human augmentations, if you have these pairs of original text and augmented text, which is augmented by like the native, I suppose we can train a model doing these augmentations instead of like humans, and that can also help in terms of how many texts we have. So yeah, I would propose doing something like this.
Thank you. No more questions?
Thank you for your talk and the project that you've done. It is really interesting. Here's what I was wondering. Your task is very similar to what Microsoft did with 5 models. instead of going on with fine tuning with every data that they can, that just sit down and clean the data first before training it, and then they produced one of the best models with smallest possible parameters. But one thing that is very interesting for me is that they highly depend on synthetic data. I just checked their synthetic data is about 40%, and then using that synthetic data, then they just better the model using the clean data. Have you had the chance to experiment with that as well, and whether you've seen any improvements while using synthetic data? And why I'm asking this, continuing to the question of Mr. Madoyan, that might be a very good way to approach low resource languages, but first we need to understand whether it actually works for high resource languages.
Yeah, actually it works. Actually, we use a lot of synthetic data for soft fine-tuning step. So I would say that all the data we use for soft fine-tuning step is synthetic generated, like synthetic sourced. And I would say that we can do the same thing for pre-training at some point. Well, I mean, like the number of data that is in a world, it is quite limited for any language, and I suppose that at some point we will meet this need to get more data to train more models that are stronger. So at some point, even for pre-train steps, I would say that we need some synthetic data that is produced somehow, and especially for low resource languages. That's just what I was talking about. Like if we have some data with augmentations, like if we can augmentate this original text and get more text for these low resource languages. So we have natural languages and augmented ones, and augmented are just synthetic data. So I would say it should work. I didn't do this for this project in terms of doing this in pre-training, because now we have enough data for pre-training this language adaptation step in Russian, but I suppose it should work, especially because it works for software.
Questions? I have a question. There was a slide with you should not.
Okay.
Okay. So about that slide with the Voronoi polygons, it's just a representation, right? Because the real dimension should be the embeddings dimension, right? It's not 2D. Voronoi polygons are in
Which slide?
multidimensional space, I guess. It was a slide about FICE optimizing, and splitting in Voronoi polygons, but it's not two-dimensional, right? It should be multidimensional.
Yeah. Voronoi cells is just like a visualization, but actually,
we just wanted to make sure that we get it right.
It is just so it's easier to explain. I mean, in terms of indexes, we use IBF index, which is implemented in FICE, but you can you can look at it as It's that's hyperdimensional, but it in terms of 2D, it looks like Voronoi cells, so it is just for the sake of visualization.
And thank you very much. It was a very dense presentation, a lot of information. It was an excellent choice to close today's session. Thank you very much.
Thank you.